Hi, my name is Sarah Jenkins, and during this summer of HPC, my project has been making quarks fly further. Okay, so what is a quark? Quarks are the fundamental building blocks which come together to form composite particles such as protons and neutrons. A proton is formed of 3 quarks, 2 up quarks and 1 down quark. These fundamental particles are bound together via the strong force. This interacts via colour charge. There are 3 different types of colour charge: red, blue, and green. Each fundamental particle carries a colour charge. In total, there are 14 fundamental particles, 6 quarks, and 8 gluons. My project was on quantum chromodynamics, which describes the forces between these quarks and gluons. Quantum chromodynamics can be described using this equation here. As you can see, the equation is very complex and therefore is not directly solvable. To solve it, you therefore need some kind of approximation. At short distances, perturbation theory is a good enough approximation. However, even on the scale of a quark confined inside a proton or a neutron, the distances between the quarks are too large to use a perturbative technique, as the forces between the quarks are too strong. This means you have to find another approximation. The one most often used is lattice quantum chromodynamics. This treats the system as a lattice of fixed points, with the quarks lying on the lattice points, and then the bosons acting between them. This simplifies the calculations, as the quarks can now only lie on the lattice points. This can now be solved using this equation, where D is an extremely large matrix and Z and B are extremely large vectors. The computational challenge comes from the fact that to get realistic results, the lattice points have to be infinitely close together, and as the lattice points become closer together, the matrices become larger and larger. This means that even for very small systems, a lot of computational power is required. The dynamical interactions of the quark field and the gauge fields are described by this equation. However, in order to use these equations, they must be discretized. This therefore assumes that the lattice spacing is non-zero, and the simulations must be extrapolated to the continuum limit. For this, the simulations must be repeated in multiple sufficiently small lattice spacings to avoid critical slowdown. So, what happens when you have to repeatedly solve very large matrices? The largest source of slowdown comes from the fact that it takes time for the computer to access the memory, and the time taken depends on where the data is stored. Ideally, you want everything to be stored in the L1 cache, as this is the fastest for the computer to access. However, as the matrix becomes larger, it will no longer all fit in the L1 cache, and will have to be stored in the L2 or L3 cache. This means the computer takes longer to access the memory. By repeatedly accessing array elements and performing simple calculations, the size of the caches was observed. As you can see, the time increases as the size of the arrays approaches the L1 and L2 caches. Okay, so now we want to calculate our program's efficiency. This is done by calculating the number of floating point operators per second, or flops. This is calculated as the total number of floating point operators over the total time. Therefore, you want to maximize the number of floating point operations per memory access and try to decrease the number of memory accesses. Calculating the flops is useful as we can quantify a program's efficiency. And from this, we can understand which functions are slowing the program down and try and quantify any improvements made. The flops were calculated for 3 different simple functions, with increasing array sizes. This is useful as in quantum chromodynamics, the array size is very important, as the array size wants to be as large as possible without increasing the flop rate too much. The peak flop rate occurs at small array sizes. As the array size becomes larger, the size of the array can no longer fit into the cache and the flop rate decreases. Therefore, the optimum point occurs here. Quantum chromodynamic simulations attempt to run in this region. This gives a good balance between array size being large and runtime being small. Next, we attempted to improve the efficiency. This was done by using assembly-level programming, specifically Intel Intrinsics. This can optimize code for a specific CPU. This has a one-to-one mapping to the assembler. Therefore, the compiler can understand the code easier and therefore can be more specific about what you want a program to do. However, as you can see, it is much more complex to program. This program is just a simple matrix multiplication. And as you can see, if you compare it to a normal matrix multiplication program, it's much more complicated. This knowledge was then used to improve the current lattice quantum chromodynamics package. The flop rate was tested to see how it copes with increases in time and volume of the space-time lattice. You can see it achieves a massive flop rate of 300 gigabytes for large lattices and times. The main achievement of this project was the great amount of knowledge that I have accumulated. As someone who came here with no knowledge of high-performance computing, this has been a very steep learning experience, but I now feel ready and able to use the techniques that I have gained throughout my PhD. For this, I would like to thank Stefan, my supervisor, and everyone else here at the JSC. Thanks a lot for listening.